junction transistors. Now up until now, what we've been doing, and I'll put two arrangements up here. Is we've been dealing with saturated switches, right, or using a transistor as a switch. So I'm going to put a resistor up here, but what you need to understand is this is just some type of DC load we can put right there. So we can put relays, we can put lights, we can put motors, small motors, big, sure enough heavy-duty motors. We have to play around with this a little bit. We can control them with transistors, but we'll show you a little bit on that later on. We've got two other devices that we use to control extremely heavy DC loads. We call these SCRs, silicon control rectifiers. Would help us control a DC device, a heavy current DC device or heavy power DC device. And then we have what we refer to as triacs, which helps us control AC loads. But what we're going to do is we're going to put our load right there, and we'll come over here and we'll put our VCC right here. And then we'll come over here and put our switch, our common right there. Now normally if we're using this for a switch, what we would do is it's very simple. Is we'd just bring whatever we're controlling this with. I would just put a switch right here. And then when I close it, whatever closes this would turn the transistor off. And when it opens, the transistor would turn on. Everybody okay there? Now, and this is, anytime we do this, this is referred to as base bias. Now what's the problem? And we could also do it like this, guys, and this would still be base bias, where I could put the resistor in series. And then I'm going to come up here, I would still put my load right here. VCC. And then what we would do over here is whatever's controlling it would come over here and do this, or something like that. Well, that still wouldn't work with it. So what would happen over here, and this would be kind of like we was using this in a digital circuit, is what's going to happen is this guy over here is going to either be like plus V or 0 V. Okay. So when I put a plus voltage over there and we design it right, it'll turn the transistor on. If we put a ground over there, it'll turn the transistor off. Is everybody okay so far? Now what's the problem with base bias? Well, we have something that semiconductors, especially transistors, want to do, and it's referred to as thermal runaway. So what would happen is that if we didn't design this thing correctly, and we didn't do what we learned to do, then what would happen was the transistor, when it started getting hot, if the temperature changes, if the temperature goes up, the beta goes up. Right? You understand that? If the beta goes up, then it conducts more current. If it conducts more current, the temperature goes up, the beta goes up. So if we don't do something about base bias is very unstable because it changes with temperature. Especially when I'm trying to run it in the active region. And this is what I hooked up the other night, and we heated that thing up. And that would be if I'm coming over here. So a better example for this, and I'm just going to hook this up without any type of control. And this is what we did the other night, if y'all remember that. So let's say VCC equals 12 volts. and I set it up. I bias the transistor so it drops 6 volts. And of course, what would this collector resistor drop? It would drop 6 volts, right? You understand? Now this is where base bias gets screwy. Because right off the bat, the transistor is conducting a current, right? You understand that? So how did this resistor up here drop 6 volts? Well, if it's a 1K resistor, then that means if it's 1K resistor, then that would require 6 milliamps. Well, down here, I've got 6 volts dropped across my resistor. As soon as 6 volts is dropped across my resistor, I get power is equal to V times I. So here we'd say power would be equal to 6 times 6 milliamps. No, 12, yeah, 1K, 6 milliamps. Well, as soon as I push a current through a voltage, what happens? What do we create? When we push when we push current through a voltage, what does that create? A voltage drop, what does that create? Huh? No, we've already got resistance. We're pushing, it produces something called P. P is equal to V times I. Well, when we push current through a resistance, it creates power in the form of heat. Well, okay, so my transistor starts heating up a little bit. Well, what happens? Well, if the transistor heats up, beta goes up. Now, what's going to happen is current will go up, which means instead of this guy dropping 6 volts, now it's going to drop 7. This right here would go to 5, and current in the circuit goes up. We push current through a voltage. What happens? It gets hotter. Beta goes up. Transistor's resistance goes down. This other resistor drops more voltage. The transistor drops less. It gets hotter. Beta goes up. Right? You understand that? So base bias will go into thermal runaway. So odds are base bias, we almost never use that with the transistor in what we call the active region. And how do we define what are the 3 regions we can occupy a transistor? We can run a transistor. Or bias would be one. What's the 3 regions we can bias a transistor to operate? Active region. Guys, this is not very saturation or cutoff. Now, if we can saturate it and guarantee it saturates, then once the transistor is saturated, then we have no problem because the current can't go up anymore, right? You understand? And when we cut it off, we have no collector to emitter current. If we have no collector to emitter current, then we don't have current flow through a voltage, right? You understand that? We have a voltage drop, so your transistor's dropping all the voltage, but there's no current flow through that voltage. So you can't have power unless you have 2 things. You got to have what? You got to have voltage, and you have to have current, right? You understand? So that means if I operate this thing as a switch and I do it right, and that's why we use the minimum beta, because minimum beta is guaranteed. So if I use minimum beta and I round that base transistor down, we don't have to worry about thermal runaway. If I tried to operate this sucker in active region, it's basically impossible. Because what would happen? In the summertime, it'd have one thing, in the wintertime it would have another, and if it started getting hot, it would do what? It would automatically go into runaway. And that's what I did the other day. I hooked up a base bias circuit. I dropped voltage across that. I ran it I biased it in the active region, and I put my soldering iron up against that thing, and we saw the voltage across the transistor started going down, and the voltage dropped across that other resistor went up. So I couldn't have a stereo amplifier, just like the little video shown, which is totally wrong. I could not do that with base bias. So what we have to do is we have to come up with a method that we can bias it that prevents thermal runaway. And we're going to work toward, the main bias we use is something called voltage divider bias, but the way the book teaches it is the way most people learn it. So what I'm on the textbook, and I'm on page 230. So you're going to need to open those textbooks. And we're not going to put an input signal on these. What we're going to do is just look at them. And then later on, we'll start putting true input signals on these amplifiers. Because an amplifier doesn't do any good. When we say amplifier, what are we trying to amplify? Anybody got any ideas? What are we trying to amplify? For transistor amplifiers, what are they trying to amplify? Power. Now we're trying to amplify power because power is what? Work. Now what we mean is we're going to take what power we put into it and then what power we get out of it, and that would be the gain, right? So we're trying to get power gain. Now to get power gain, we got to do one of two things. We got to get a higher voltage signal out than we put in, or we got to get more current out than we put in, right? You understand? So we're going to have to gain one of those because the only way power is equal to V times I. So there's no such thing as just power. I can't have power unless I have what? Voltage and current. Does that make sense? So what our amplifiers are going to do, well, they're going to either amplify the what? The voltage, or they'll amplify the what? Current, or some of them amplify both. And that's what we'll look at. So what we do is we come up here and we do a little neat little thing. Is we come over here, so I'm on page, we're going to look at what we call emitter bias. Y'all see that in the book? So emitter bias, what we're going to do is we'll draw that same little circuit, and we'll look at some neat stuff we can do with emitter bias. I'm going to put a resistor down here in the emitter. So this takes a little bit of design, but what I would do is, now we're not dealing with 7/10 of a volt. Well, let's say just make up a voltage. Let's say I bias this or come down through here, and then this sets this at 4 volts right there. Well, this across this emitter resistor, then across the emitter resistor, what would be the voltage across the emitter resistor? First of all, is the transistor forward bias? Yes. The base is pointing toward the positive, and the emitter is pointing toward the negative, right? You understand that? So this guy here, we're almost there on turning it off. We got to do something else first. So let's say I'm putting plus 12 volts there. So what would be the voltage drop across the emitter resistor? Come on, what would be the voltage drop across this resistor right here? We're going to call it RE. Right now we'll call this RB, and we'll call this RC. So what would be VR? What would be VRE? Somebody take a guess. Huh? Okay. 4 volts. Kirchhoff's voltage law says the sums of the voltage drops in a series string has to equal to the applied voltage. So right now I know this resistor right here is dropping 8 volts. Is the transistor forward biased? Yes or no? Is the base putting toward the pot? Okay. So that means I have a diode right here. I have a P-N junction right there. So what's the P-N junction going to drop? If it's silicon. What's the P-N junction going to drop if it's silicon? What do we use, guys? Okay, so I'm going to put 0.7 tenths. So what would RE drop? So I've got 8 volts plus 0.7. I'm going to subtract that from 12. Of course, you don't really have to do that. You can subtract that from 4. And what does that leave? Is this math real hard? 3.3 volts. Okay. All right, so 3.3 volts on the emitter. And of course, up here, we got whatever's left over there. Okay. So that means what's going to happen? Well, what if I come up here and let's say whatever this resistor is right here, we're setting at not 6 volts. Let's say, let's say this is setting at 6 volts. So the transistor is dropping about 2.7 volts. So we're conducting current. This guy up here is dropping 6 volts. My transistor and this emitter resistor, this is dropping 6 volts because it's the sum of the two, right? So Kirchhoff's law says the voltage in a series string, so here's a series string, has to equal to the applied voltage. If this guy's dropping 6 volts, that leaves me 6 volts right there. This guy's dropping 3.3, so the transistor's dropping 2.7. So there's current flow through the circuit. Okay, as soon as I get current flow through that voltage drop in that resistor, in that transistor, I have I and I have a V. It's going to start getting hot. Beta is going to try to go up. Can beta go up? How? This guy right here cannot move. This voltage is set by that. That voltage is set by that 4 volts. That 3.3 volts cannot change. So if the base current if the collector to emitter current tries to go up, it means this resistor right here would have to drop more voltage. That resistor can drop more voltage because that is not set by that current. That voltage is set by that resistor right there, right? By that voltage right there. So what would happen? So if we beta would try to go up. If beta tried to go up, the collector current and emitter current would try to go up. It would try to make this resistor drop more voltage. That resistor can't drop more voltage because that voltage is set by the base. Well, what if the temperature went down? Well, beta would try to go down. Well, beta can't go down because if beta went down, this guy right here would drop less voltage. It can drop less voltage. It's got to drop what? 3.3 because that's set by the 4 volts on the base. So this guy absolutely will not go into thermal runaway. It'll sit there fat, dumb, and happy all the time, right? You understand? Because it's what? It's not depending on the collector current to set that voltage. It's depending on the whatever's over on the base. Y'all understand that? So putting that resistor in that emitter causes some really neat things to happen. Are we okay? Do y'all understand that? So if beta tries to go up, can beta go up? Well, if beta goes up, so IC, according to this, IC is equal to beta times IB. Well, what would happen is beta would try to go up, but beta can't go up. Because if IC went up, what would happen? This resistor right here would try to drop more voltage. And it can't because it's set by what? It's set by that voltage right there. Y'all understand? Yes or no? Which is pretty neat. So beta can't change. So this guy here absolutely would not work, and it would not work in thermal runaway. The problem we have is that we would have problems using this as a switch. So we can't use this as a switch. That's the role of the common base, right? I mean, I'm not common base. The base bias. So base bias is great for a switch. It's just crummy as an amplifier. This guy works real good as an amplifier, but it's still got a few little problems. And this is called what? This is called emitter bias. I made it up. I was trying to figure out how what I did first is I made up the 4 volts. And then I used Kirchhoff's law in my head. I said, okay, if I got 12 volts right here, and I got 4 volts right there, because Rich made that up, then this guy right here has got to be dropping what? So that's 12, 4. That means this guy, so I go from 12 to 4. What's the difference between 12 and 4? 8. So that means this resistor right here is dropping what? 8 volts. And we're just doing this with voltages because it would take me a little while to calculate the resistors. We could do it. But right now we don't really we just need to understand what we're trying to do is we're not trying to teach calculating circuits. We're trying to teach biasing circuits, different ways we bias a circuit. Okay, Charles? And then if I have 4 right there, then this guy right here drops 7/10 according to Kirchhoff's law. And if I was to draw this circuit up there back in DC and I put 8 volts and 7/10 of a volt, and you said what would be this resistor over here, y'all have no problem. So if I would have came back here on DC and I would have drawn it like this, and I'd have came over here and say, oh, this is 12 volts. I come over here, got this. I said, this guy right here is dropping, this guy right here is dropping what? 8. This guy right here is dropping 0.7. And then I came over and say, what would be the voltage drop right there? what would be, so I'm calling this is RB, of course this is the diode, this is RE. Now what you got to understand is we got, in a transistor, we got two different circuits. So this is one of our series loops right here. I mean our series path right there. And this is our other series path right here. So what you got to learn is that we treat these two paths separately. The only thing that we use from this path over to this path is this 0.7 of a volt. So that's this sets the voltage on that resistor right there. But once I did that, then I'm through with that. Right? You understand? So I made up this 6 volts right here too. I said we got 6 volts there. So that means RC is dropping 6 volts. This guy's dropping 3.3. So that means the transistor's left with what? 2.7. And that would have been just back, where did y'all learn how to do that? Where did y'all learn Kirchhoff's voltage law of a series circuit at? Or a series string. Here we're just applying that same law, but what's neat about this is we got two series strings, and it looks like they're combined. And they are, but electrically we can treat them as one. It's two different circuits, which is pretty neat. So when I come over here later on, and so this is what we're working on, guys. We're working on this guy right here. This is the most popular way of biasing a transistor in the active region. Is this right here, where you can see this right here, that right there is emitter bias. And what's that guy in there for? To keep the transistor from going into what? Thermal runaway. That's what that guy's in there for. Because if the collector current tried to go up, it can't go up because that voltage is clamped by the base, by whatever voltage we put on the base. And we'll see how this works. This is called a common emitter amplifier. This is one of the most popular amplifiers in audio because it gives us both a voltage and a current gain. But it's got some problems. So we have two arrangements that we use a lot. We talked about this the other day. And one of them is called a common emitter, and the other one's called a common collector. And then we got a common base we'll just glance at. But you're not going to run into the common base almost none. So we'll put most of our into that. And you already know that circuit. So what I would do is I would come up here and calculate that circuit just like this. I would look at this string over here, and I would calculate that like a series circuit. And then I'm going to move over to this string, and I'm using that to represent the transistor, and I would calculate that string. And y'all can calculate this right now. I mean, you can do it. You know, if I gave you the size of those resistors, you could calculate the voltage drop right there. You'd subtract 0.7 of a volt. That would give you the voltage drop across the emitter resistor. Once you got a voltage drop across the emitter resistor and you know the size of the resistor, you can calculate IE. And what do we assume about IE and IC? What's the assumption we're going to make? Huh? Equal. We're going to assume they're equal, even though they're not. They're so close. So if I know IE, I'm going to use that for IC, and then I can use IC to calculate the voltage drop across this resistor. If I calculate the voltage drop across that one, I know the voltage drop across that one, then I can use Kirchhoff's law to calculate the voltage drop across the transistor, and we've calculated the bias on that one, using nothing but what? And this guy, and what's neat is we never used beta. And what's the problem with beta? What's the problem with beta, guys? So get on Blackboard and look up the beta for a 3904 transistor. You tell me the problem with beta. That beta can be anywhere between 30 and 300. So what we'll do with this circuit is we'll set the beta of the circuit. We'll set the beta of the transistor. All we got to do is just make sure we don't exceed 300, right? So we'll set it around 100, 150. That way it'll give us both ways. But we'll set the beta this circuit. So all we got to do is set it somewhere between the minimum and the maximum. On a transistor switch, we don't set the beta. And that's why we got to use the minimum beta, because that's the only beta that's guaranteed, right? You understand? So that's why we use that to calculate our saturated switch, and then we don't have to worry about thermal runaway, because if beta tries to go up, the dang transistor's saturated. And when it's saturated, it's turned on wide open already, right? You understand? So emitter bias. Very, very stable. So we got base bias, we got emitter bias. What do you think the third bias would be? Huh? Collector bias. So let's look at collector bias. This is probably one of the most least used, but it works on the same basic principle. So what we're going to do on collector bias is we're going to come over here, we're going to put our collector resistor. Then what we're going to do is we're going to take our base biasing resistor, and we're going to hook it off a connector right here. And we'll just do this like a voltage divider. So this would be 6, this would be 5.3 because of the 7/10 right there, right? Okay, so we're in active transition. If I have 6 volts right here, that means my voltage collector to emitter is equal to 6 volts. So how do we identify the region? What do we use to identify what region the transistor is operating in? No, but we use a voltage. We use the voltage collector to emitter. If it's less than 1 volt, we assume it's saturated. If it's equal to VCC, we say it's cut off. If it's somewhere between 1 and VCC, we say it's an active region. So here we're measuring a voltage collector to emitter of 6. If it was cut off, it would be 12. If it was saturated, it would be less than 1 volt, right? You understand? I think the 3904, the maximum I said it would be like 600 millivolts, I think. We can look at the data sheet. Okay, so how is this guy going to prevent the thing from going into thermal runaway? What's going to happen if IC goes up? Well, this guy right here sets the base current. That 5.3 volts sets the base current. So if IC tries to go up, RC is going to drop. So let's identify these resistors. So we'll call this RC and we'll call this RB. And right now we don't have an RE. So that resistor sets that voltage right there. If that resistor drops more voltage, this voltage goes down. This voltage controls the base current. So if the transistor tried to run away, IC would go up. If IC went up, this resistor right here would drop more voltage. If this resistor right here tried to drop more voltage, this 5.3 volts would go down. This guy's controlling the base current. The base current would go down and maintain the same voltage, right? You understand? So if this voltage right here tried to change, if it tried to go down, right, you understand, it would turn the transistor off a little bit. If it tried to go up, it would turn the transistor on a little bit. So it means if beta tried to go down, this resistor right here would drop less voltage. This 5.3 volts would get bigger. It would cause more base current. Base current would turn the transistor back on. So this guy here would be just flat, sit there just no matter what the temperature was, until you burn the transistor up or until you froze it. It would sit there and maintain whatever beta we had set. So these are the 3 ways we can bias. Base bias. The problem with base bias, we have a problem with thermal runaway, so we use that only as a switch. We call them saturated switches, even though basically to run a transistor as a switch, we actually cut it between two regions. We saturate it or we cut it off, right? So that's a transistor switch. And guys, you're going to run into things all over the place. Because we get a pretty good current gain out of them, and we can control that sucker electronically. So my programmable logic controller can turn things on and turn things off, right? So a lot of your, if you got a DC output module on a PLC, it's going to use a saturated switch. It's going to use a transistor. And we won't talk about that in this class. So there's our three methods of biasing a transistor, and then we have the main one, we call it voltage divider bias, which is basically a combination of a base bias and emitter bias. Collector bias problem is that your collector voltage is all over the place. So if I get my output off my transistor, so let's say I'm taking my output off here and I'm sending this out to the outside world. Well, the problem is while it's monitoring, while it's trying to maintain it, the collector voltage is trying to move around, right? So that's the problem we have there. So we lose some of our collector voltage. Huh? We'd use it because it only requires two transistors. This will be if we're trying to operate in what we call the active region. So sometimes we have a problem. So let's say, and we've ran into this before, is that we had a 20 volt, we had a 12 volt relay, but the only source we had was a 24 volt source. So we had a 12 volt relay, but we only had a 24 volt source. So what we could do, and then of course relays are rated in two different things. They're usually rated in volts and amps. Most of them are rated in volts and ohms. So we can make up something. So let's say we looked at our relay and it says that the coil had 800 ohms worth of resistance. And what I'm going to do is I'm going to come over here and I'm going to put my relay right here. Okay. And then what we'll do is make sure we put that counter EMF diode in there, right? Because if we didn't, we could bop our transistor. And we know this guy right here is we want it, it's rated at, I got this backwards. So my relay is rated at 12 volts at this, but the only supply I have is 24 volts. So what could we do? This is not the way we did it. I'll show you the way we did it. Well, what I could do is I could design my transistor, and I could use collector bias. So what I would do is I would hit my transistor right there, and I could set my transistor up to drop 12 volts. Then I could come up here and put a switch right here, or whatever's going to switch it would be right here. So when that switch closed, no, that wouldn't work. The transistor would cut off, but the relay would still get current, so that wouldn't work. I'd have to figure that out. But this is not the way we did it. I'll show you the way we did it. But this would be one application. So anytime I'm trying to do something where I want to operate the transistor in the active region, if I'm going to operate it in the active region, then what would I do? I would either use what? Collector bias. I would use what? Emitter bias. Because we could do that with emitter bias too. Well, but that emitter bias is so neat because what would happen is so voltage divider bias takes four resistors. Collector bias takes two. Listen, Brian. So anytime I'm I'm not getting a lot of power and I just want to operate the transistor in the active region for some reason, then we need to use emitter bias or collector bias. If I'm trying to get a lot of power and get really, really good control, thermal control, then we'll use what we call voltage divider bias. See, voltage divider bias requires at least 4 resistors, right? The one I just drew on here. The way we did it was this way. And y'all could calculate this. This is pretty easy. So we did it this way. So we put our relay right here. And then we put a fixed resistor right there. And then of course, don't forget the diode. Y'all know about the diode, right? We went into the went into the room right there and looked at that inductor. A relay is nothing but a bunch of coils of wire. But instead of using it as an inductor, we use that coils of wire to generate a magnetic field. And that magnetic field brings in contact force. But the problem is when you de-energize that thing, it outputs that voltage. And ours wasn't as much voltage as we would see on some of these DC relays, because some of these DC relays, the only way they get R is through the number of turns of wire. Because there's no real resistor in the relay, right? You understand? So they got to use a lot of turns of wire, fine gauge wire. And when that magnetic field comes collapsing back into a bunch of turns, then it's going to induce a counter EMF that'll flat wipe out your transistor. They'll exceed the breakover voltage G. So this is what we did. So what we did is we came over here and we had the we were running off 24 volts. And I don't forgot what transistor I used, but we'll make up something. And then my resistor, I said it needed what? 12 volts at 800 ohms. So what would we do? And let's come over here and go ahead and we'll do it like this. And what's real neat is I can run it off of like 5 volts. So we'll call this RC, we'll call this RB, and you already know everything. You know everything you need to know to calculate this. And I need to give you a beta, right? So let's use a minimum, let's do a beta of between 30, my beta is between 30 and 200. Okay guys, how would we start? Somebody tell me. Where we're going to start at? I'm going to start where I know something's at. I know, the only thing I know right now is the relay. The relay. I know it is what? It's going to run at 12 volts and it's 100 ohms. Well, what can I calculate? Using Ohm's law, what can I calculate? I can calculate the current, good. So I can come up here and calculate current. So I can say my current, which is going to be IC, and this is going to be the saturated current, would be equal to 12 divided by 800 ohms. So what's my saturated current? That's what I want to do. I'm going to saturate this transistor. We're going to run this as a saturated switch. What would be my saturated collector current? Huh? 50 milli. Okay. Okay, so I just calculated that. So what do I know now? What do I know about RC? I have 24 volts at the top of it. I got 12 volts at the bottom of it. What do I know about RC? It's going to drop. Kirchhoff's voltage law says the sums of the voltage drop in a series string. We're going to set our transistor up. We're going to assume it's saturated. It's going to drop 0 volts, right? You understand? So the transistor is acting like a closed switch. So we're not going to worry about that guy. If this guy here is dropping 12 volts, what's this guy right here got to drop? 12 volts. At what current? It's in series, right? So RC, and what's the formula? R is equal to V over I. So what size would we use for RC? What's that? And if it was a standard resistor, that's what we'd use. If it wasn't, we'd round it. Not round up, round out. We'll just round it to the nearest quantity. Odds are if the thing's right, needs 15 amps, it'll work it a little more. It'll actually work it a little less. Okay, guys. So what does that tell me? So now I need 15 milliamps over here. My beta is between 30 and 200. So what do we know now? So we got to work on RB over there. Yeah, we're working on RB. How much voltage is RB going to drop? Got 5 volts on the left. My transistor's going to drop 7/10. Got 5 volts on the left. Got 4.3. So I know RB is going to drop 4.3. But I can't calculate RB unless I know IB. So how do we know IB? So we're not learning anything this class. Well, I know beta is equal to IC over IB. That's one of those formulas I shouldn't have to give you now. Okay, so I just rearranged this a little bit to solve for IB. So IB is going to be equal to what? IC over beta. Okay, so I'm going to say IB is equal to, what's our saturated current over here? 5 milli over 30. Beta's 30. We use minimum beta. Why do we use minimum beta? Because it is guaranteed. 200 is not guaranteed on a saturated switch. So I'm going to come up here and I say, okay, and this is going to give me what we call IB sat. This is the saturation current required to saturate it. We can saturate it, we can't saturate it more, but we never, ever, ever want to get below this. Because if I got below IB sat, the saturated base current, saturation is no longer guaranteed. As soon as I get below 30, it's not guaranteed. I mean, as soon as I get above 30, it's not guaranteed anymore, right? You understand?
As you move down, the base or the resistance, right here for our base six, you should already know the base beta should be 30.
Well, no, I gave you right here before we even started. I gave you the beta. I said, okay, the beta of this transistor, we looked it up on our data sheet, and it says it's somewhere between 30 and 200. Okay. And then, of course, what are we going to use? Yeah, we're going to use the minimum beta. Yeah, so we gave you that right in the first. See my little beta symbol right there? Okay, so what size base resistor would I use? God, I hope not. R is equal to V over I. Here we're going to be I. This is going to be our calculated. So the only formula that you've learned new is beta. That's the only formula. Everything we've done it with what? Kirchhoff's law, right? And Ohm's law. And this is a simple gain formula. Guys, we're going to be dealing with gain formulas all term long. 9.1? 1K? K, right? Yes? Huh? I don't know. 50 millis, so it'd be 0.015. And divided by 30 equals 0.015. Divided by 30 equals, why are you doing that? course, I could have done that in my head. Right, and I'm going to divide that into 4.3. Swap them around, equals that. I got 8.4. 8.2 would be the standard. It calculates to be, and that's what I was going to say. We always round this one down, right? Are you okay? So this is what we did. So all we did was chose a resistor. I forgot what it was. But we did this exact math. So we hooked that little transistor in there. I'm not going to tell you exactly what we did. This is one way we could calculate it. We were actually running this on a PLC. So the actual circuit was this. And then we had the relay. And then we had the diode. And then we went to the output on the PLC. So that's what we did. But bringing the transistor in there was pretty good. And that's not exactly what it was either. The output of the PLC was actually up here. So what the PLC got us, it either gave us 0 or it gave us plus 24 volts up there. But we did the same math. You know? So all we did, and we didn't know we knew the voltage on the relay, but it didn't give us the resistance. So we got our ohm meter out and measured the coil of the resistance, and that gave us the R of the coil. And then we did the math just like we did on this side. So this is the way this is what we actually did. So we had a 12 volt relay, but the output on the PLC was 24 volts. Another thing that you can do with emitter bias Now this is not running saturation, but this is so cool, and I've used this several times. Is I could come over here, and I'm gonna put a resistor right there. And what I'm gonna do is I'm gonna put 5 volts right there. So that resistor right there would drop 4.3 volts. And we'll do it a little different. And then if this was 1K, that would be 4.3 milliamps, right? Over on this side. And then what I can do is I can come over here and start putting loads in there. And let's say this was 24 volts up here. And this was 1K. So how much would the resistor drop? How did I do that? I got that keyboard tangled up in my foot. You know what happened. So how much would that resistor up there drop? Okay, how did you come up with that? Well, you're forgetting about the transistor. This transistor is not saturated. This guy's dropping 4.3. It set this current right there. So that resistor right there set that current. Okay, so how much would this guy up here drop? Well, this guy's going to drop 4.3 volts. You don't understand that? And the transistor down here is going to drop whatever's left. So what would be my voltage collector to emitter? .3 volts. That'd be 12 minus 4.3 minus 8.6. What would that be? Series circuit, right, guys? And this is the problem. For some reason, y'all get scared of the dang transistor. You don't realize that a transistor can drop voltage. And that's a series string. If I was to come up here and do this, if I was to draw this circuit right here, and I said plus 24, I said 4.3 right here, 4.3 right there, and I ask you how much with this guy right here dropping, you would tell me right off the bat. You would just do what? You just add, okay, so what is it? And this is the problem, is you don't see the transistor like that. So how much would my voltage collector emitter be? Huh? So it's going to be 24 minus 8.6. So what? Huh? 15.4. Okay, so let's say I come up here. Oh, darn it. I erased all of it. But that's okay. Don't take long to draw. I'm going to put another resistor up there. And this is the 1K, and this is the 1K. I'm going to come over here and put a 1K down here. I'm going to come over here and I'm going to put plus 5 volts on the base. Plus 5 volts, that means this guy here is going to drop 4.3 volts. I'm going to divide that by 1K. It's going to give me 4.3 milliamps. And up here I got plus 24 volts. How much is this resistor going to drop? 4.3. How much is this going to drop? 4.3. How much is the transistor going to drop? 11.1. Well, what would happen? No, I'm not changing the both. This is what we call a constant current source. So what I do, if I was to clamp the base at a voltage and then put an emitter resistor over there, I don't care what I do over here, as long as I don't exceed, as long as I don't make all these drop 24 volts, then it would be saturated. Then this transistor would automatically adjust its resistance to maintain that exact current. So I've seen this a lot, like in burglar alarms, where people want to put LEDs all over their car. They say hook them in series. Well, what are you doing? Well, what they got is they got a constant current source. It's set up for 15 milliamps, and you can string those suckers. You can string as many LEDs as you want to. You don't have to put resistors on them because we're setting the current with that base resistor, right? So let's see. I don't know what that would be. So what would be what size resistor would I need here to 4.3 at about 15 milliamps. So R would be equal to that. So what size resistor would I use right there? I'm listening. 270, that's a standard size too. So I'm gonna save this. That's good. That's good because 15. Most of them will conduct more, but that's good. 270 ohms. Well, I could come over here and I could put a diode right there. I could put one diode and connect it up to 30 volts. It don't make any difference. Or later on, I could come back and do what? Add another one. Later on, I could come up here and add another one. Later on, I could come up here and add another one. And how long could I go? Well, I could go until all those diodes dropped all the volts. Because the collector current would be set by that resistor right there. And we call these constant current sources. And this is what your meter's using when you put it on ohms. So when you put it on ohms, digital meters are a constant current source. It's usually around 1-2 milliamps. And then what it does is it steps the voltage up. It automatically steps the voltage up until 1 milliamp flows, and then it measures whatever voltage is required to cause that flow, and then it displays that in what? In ohms. So you got to understand the measurement unit inside the meter only measures one thing. It measures the difference in potential. So that's why when we do ammeters, we use a resistor we call a shunt resistor. We already talked about that, right? Did I show y'all the inside of this meter? You actually see the shunts. So it's just a piece of wire that drops the voltage, and then the meter measures the voltage and interprets that as what? As amps. I'll take the stereo apart and I'll show y'all the shunting. We got a shunt over there. I'll show y'all. So most of the time, when you got an amp meter up on a panel gauge or something, we don't bring 5,000 amps up into that little. We put a shunt out there, and it runs through the shunt, and you're measuring the voltage. Your meter's measuring the voltage drop across the shunt. Are y'all guys okay? There's another thing, a couple more things I wanted to show you. And then we'll go to lab. And we got a worksheet, by the way, on saturated switches. I need to make sure I do that. What do we call this when we move transistors like that? What's it called? Good. It's called a Darlington pair or Darlington. It's called a Darlington. They called it a pair. They called it an arrangement. Or they misnamed it and called it a Darlington transistor. So when you look at these things, you still got a pack. It looks like this. It's got 3 leads coming out of it. One of them's going to be the base, one of them's going to be the collector over here, one of them's going to be the emitter on your output transistor. Now, what's the advantage of this? Yeah, it multiplies the beta. And it's got another big advantage, too. So if this had a minimum beta of 100 and this had a minimum beta of 100, then what would be my total beta? Huh? What's that? This one had a beta of 100 and this one had a beta of 100. What would my total beta? 3,000? I can't take 3 times 3 and come up with 3. Huh? What's it going to be? So this is going to be 30 times 30, which would be what? 900, yeah. So that would be the total beta of this. So you can get Darlington pairs with beta, it's over 1,000. Real easy. Real easy. And what's nice about this, and another thing I wanted to show y'all too, is that the problem we have with the problem that we have with the Zener regulator is the amount of load current that it can handle. Right, you understand that? But let's say this is my unregulated right here. Well, what if I came over here and did this? And this right here was V out. How much collector current could we handle? How much current could we handle now? Huh? No, all the Zener's doing is providing base current. And the Zener's not even providing base current. The base current is being provided by this resistor right here. All the Zener's doing is adjusting it to maintain this voltage across there. So what we're saying is we come up here and, if this right here is set at 5.6 volts, what would be the output voltage? Now I'm gonna have to hook this up to a load, guys, so it won't work. What would be my output voltage? It'd be around 4.9 volts. So this would be a really good 5-volt supply. But what I've got is my Zener is no longer supplying load current. My Zener is providing base current. And what do we get between? So what we do is we get the gain of the transistor, right? You understand? So we come over here, and it all depends on the beta of the transistor, how much collector current you can get. But what if I did this? And I've built several power supplies like this guy. So if these both had a beta of 30, but that's the minimum beta, you know they're going to have a beta bigger than that, right? You understand? Then that means this right here would have a beta of 900, right? You understand? So that means I could get 900 milliamps over here for 1 milliamp of current right there. By the way, in power supplies, we call this transistor right here, we call it the series pass. And then I would hit my load right there. And you're going to see a lot of and this would be my unregulated end. This would be my regulated out. Now what I'm going to have to do though is I'm going to have to choose a Zener that's got a VF, a VZ of about 1.4 volts greater than what I'm trying to get out. Because here's my path right here, right? So that means if I wanted 5 volts out, then I would have to find a Zener that had a VZ of pretty close to 6.2 volts. I mean, yeah, 6.4 volts. You understand that? Man, you'll see these little power supplies all over the place. And by the way, but this guy here, you'd use a low current transistor like what we're using, a 2N3904, which can handle up to 200 milliamps. And then up here, you'd use a big guy like a 2N 3055. This guy here is rated at 15 amps, and we need to talk about that too. You'll never get 15 amps out of it because we have two ratings on the transistor we're concerned with. This right here, this is called IC max. So this is what you should expect when you saturate the transistor. But here the transistor is not going to be saturated, it's going to be in the active region. So what we do after that, we look at a rating on a transistor that we call, there's two ratings you're going to look on a transistor when you try to figure out where it's going to operate in the active region. Well, there's one you use for a saturated switch, let me rephrase that, and there's another one you use for active region. See if y'all can figure out which one. And so let's look up do I have a 3055 in here? No. We'll just look at a 3904. That's the very small one. Well, we're going to look at the absolute maximum. No, that's not the one I'm looking at. Okay. So the maximum current we can get out of this thing is 200 milliamps, but that's if you saturate the transistor. So that means the transistor is dropping almost no voltage, right? You understand that? So which rating, if we operated in the active region, which one are we going to move to? If we're operating in that active region, we're not getting 200 milliamps. So which one would you think we would use? Now see that? You can blow it up a little bit? I think I can blow it up. Dang it. I guess I won't hit this with finger. Oh, I'm hitting the wrong button. Sorry, guys. There we go. So what would you think we would use if we operate a transistor in the active region? Huh? That's the operating temperature that we can operate it in, but that's not one I'm looking for. So if we're operating the transistor in the active region, it's dropping a voltage. If we push a current through a voltage, it creates P, power. So if we operate in the active region, this is the guy right here we're looking at. How much power can that thing dissipate? Right, you understand that? And then what you have to know is what voltage range you're going to run at, and what we call the ambient temperature. Y'all know what what's ambient temperature? What did we say? What's ambient temperature? What does the term ambient temperature mean? Yeah, that's the temperature surrounding the device. So what we would do is this guy here is rated at 3904. The standard 3904 is rated at 625 milliwatts. This version is rated at 350. This version is rated at 1,000 milliwatts. But over here it says you need to do what? You need to dirate it 5 milliwatts for every degree you're above 25 degrees centigrade. Dirate means decrease by the way when you see that. So just about all solid state devices is going to give you an operating temperature. And 25 degrees centigrade is pretty standard for solid state devices. So let's get that into Fahrenheit. How will we get that to Fahrenheit, guys? Well, if you got an application on your phone, which I do, you can convert units, right? Unfortunately, we live in the U.S. customary standard of measurements, and the rest of the world is not on what we're on. And you'll see this in data sheets. So even though some of these guys are still made over here, I've never seen a solid state data sheet use Fahrenheit. They use Celsius. But the problem is we understand Fahrenheit, so we need to have a pretty good idea of what this is, right? What would this be? How would we do that? Anybody remember or know? What's that? Well, what we have, if you look at the Fahrenheit scale, for every 9 dashes on the Fahrenheit scale, there's 5 dashes on the centigrade scale. So the ratio between the two halves is either 5/9 or 9/5, depending on which way you're going. So if I'm going from centigrade to Fahrenheit, we'll multiply it by 9/5. If we're going from Fahrenheit to centigrade, we will multiply it by 5/9. Right? You understand? But remember, the Fahrenheit scale, freezing is at 32 degrees. and on the centigrade scale, freezing is 0. So we got to compensate for that. We got to set them both at where we set them at 0. So basically what we do, if I'm going to centigrade, what I'm going to do is I'm going to take 25, and I'm going to multiply that by 1.8, which is 9/5. And then I'm going to come up here and I'm going to add 32 to it. So about 77 degrees centigrade, about 77 degrees Fahrenheit would be the same as what? 25 degrees. So if I'm going to operate it above 77 degrees Fahrenheit, then we're going to have to do what? We're going to have to dirate that thing. 5 milliwatts per every degree above that. Now, if we're operating it below 77 degrees, you could actually get more power out of it. So what you could do, you could actually increase it by 5 milliwatts for every degree below 77, right? Y'all understand that? If you're going to permanently operate that. So if I was going to operate this in the active region, what I would do is I would figure out the current required by my load. I would figure out the maximum voltage my transistor would have to drop, right? You understand that? I would calculate the power, and I would find a transistor that more than doubles that capability. Using what? Using that guy right there. More than double. Okay, but double would be, because you got to understand there's a lot going on there, and that's the transistor I would choose if I'm going to operate it in what. So if I'm going to operate it in as a switch, I'm going to use this guy right here. If I'm going to operate it in the active region, I'm going to use this guy right here to calculate what transistor I'm in. So we'll use two things. We'll use the gain and we'll use the wattage rating of the transistor to figure out what we want. So we said the 3055 was rated at 15 amps. Now that's if you saturate it. If I make it drop a voltage, then I'm going to have to calculate, right? You understand that? And a lot of transistors, they'll specify that it has to be heat sinking. Y'all understand heat sinking, right? Are you okay? Heat sink. Maureen, you okay? You don't understand heat sinking? Well, let's go on the internet, and we're pretty still left out. Let's go on the internet and look at heat sinks. What determines how much heat a device can get rid of? The size exposed to the atmosphere, right? What's exposed to it, right? Of course, how the air flows across it. And then, of course, the thermal resistance between what's generating the heat to the surface that's exposed to the air. So we calculate thermal circuits just like we do using Ohm's law. And instead of using a current resistance, we use a thermal resistance. So every material's got a thermal resistance. And that would tell us how much heat it would and what we're trying to do is get as much heat from the device to the surface. Well, what they do is that they're trying to make their solid state devices as small as they possibly can for the heat they got to handle. A lot of them is the size of the device will not handle the heat that you're going to operate that in. So what we do is we come up with some method to increase the surface area. So we use devices called heat sinks, which are usually made out of metal. And basically, what's the best conductor of heat? Silver. What's the second best? Copper. Was one of the most widely used. Aluminum, and why is that? Cheap, yeah, and it's light too. And all we can do is maybe add another fin or something to the sink. But you get people that in microprocessors, and they're overclocking those things, running them a lot faster than what they intended to run them. And they'll buy those copper heat sinks. You know, they'll be paying $100 for a heat sink. But they do it if they try to do that kind of stuff. So yeah, you can get heat sinks made out of copper, but most of the time we use aluminum. Or we use steel. Steel's okay. A lot of times we actually use the surface of the metal that it's enclosed in, and we'll take the power. We'll take one of the trainers. We did take the trainer apart, right? Yeah. And what they usually are is they're usually thin. And what they fit, huh? It's made out of a silicon compound. And you know the function of the page, right? Huh? Well, the problem is that I've got a metal thing and it's almost impossible to get something perfectly flat. So I've got two chunks of metal that I'm trying to transfer heat between. So I've got two chunks of metal I'm trying to transfer heat between. I got my solid state device, which looks like this if I was to blow it up. And then I got my heat sink, which looks like this when I try to blow it up. Well, the problem is the only place we're transferring heat is where the two devices touch. So we got to have something that's got a real low thermal resistance that fills in the gap. So we can buy thermal insulators, which are rubber, which are really neat, or we can use a paste. It's usually white. It's called heat sink compound. And what you do is you put that on your you put it on your surface, and then what does it do, Brian? It fills in that gap. So it's not really bonding it together. What it's doing is it's filling in the gap. And so now what we do is we get maximum transfer between my solid state device and the metal that's doing that. But heat sinks are going to be thin. So the ones that go around transistors, they have a bunch of usually have a fin that comes out like that. The one that goes on integrated circuits are usually rectangular, and then I'll have a bunch of fins. Now the purpose of the fins though is to create a lot of surface area with very little space. And that's the way we fin everything, is because if you look at motors that's got heat sink, they got fins on them. Because if they didn't do that, and every surface of that fin is getting rid of heat. And then we try to mount them vertical, guys. So what would happen is when they heat up, by convection, they will do what? They will literally pull the air, make the air flow up through, which is the way, if you've got a radiator in the house, that's the way your radiator works. It's got fins on it, and you go over there, you can feel the cold air coming in on the bottom and doing what? Automatically pulling them up through there. The problem with microprocessors is we mount those things all over the place. So what they do is they'll put a fan assembly on it to actually blow air across that thing and really increase the efficiency of the heat sink. Your microprocessors are almost 100 watts now power. If you got a sure enough microprocessor, we're not talking about the little ones they got in your cell phones. Those are still limited by temperature. But if you got a desktop computer where you got a bunch of, you'll see that your microprocessor is an extremely big fan on it. Those guys are running 75, 100 watts worth of power, but them suckers are up in the gigahertz range of operation speed. So that's what heat sinks are. And you got the paste you can buy. What you need to do is you need to, put it in it. By the way, don't get it on your clothes. And then we do have thermal compatible insulators. The problem we have with a bunch of our big transistors, these TO3s, is the outside of the case, and I'll do the best job. The outside of the case is electrically hot. So that means this whole case right here is the collector. Well, if I've got a piece of metal on my mounted, odds are this piece of metal is going to be referenced to circuit common. So the problem is if I was to put my transistor onto that metal, I create a short circuit. So what we do is you'll see they have holes drilled in this thing. And then what we do is we put special insulators in here. I'll have to show it to you. And then we have a mounting socket. We'll pop one of the trainers across and let you see how they isolate that. And then then you put an insulator under your transistor. Mica is a very often used insulator because it has a real thermal resistance. More and more they're going to a silicon-based silicon-based thing, because it's a good thermal heater too, and it's a good insulator. But I'll show y'all that. We'll pop that off. What we'll do is we'll pop one of the trainers apart, and we'll pull the 5-volt regulator off there and let you see that and see some heat sinks. But you can get some pretty good heat sinks, guys. You look at some of these power drive circuits, you're going to see some huge heat sinks on those. And what it does, it allows us to keep our components very small, and then we use these finned heat sinks to help us get rid of that heat. Okay, guys, y'all go ahead and take a break.